Okay, so where we stop off, we just finished constructing the shear force diagram. And what I mentioned is I want you all to note when x is equal to 0.8 and x is equal to 2.4, right? The shear force is equal to 0. I want you to look at those 2 points where it goes from negative shear to positive shear at 0.8 and at 2.4 from positive to negative shear. Okay, now just take note of those 2 points first. Next, we are going to look at bending moment diagram. Okay, bending moment diagram. Just to let you know, there are commercial software doing this. Okay, there are software that has been developed just to sketch the bending moment and shear force diagram. There are entire packages, software package that could do what I'm teaching now, okay, to determine principal stress. Okay, commercially available. They're not cheap though. Anyway, we're going to sketch our bending moment diagram. So m as a function of x. So we have 48, 40, 32, 24, 16, 8, 0, 8, and ooh, I need a bit more. Okay, I need to go to 16. Okay, minus 16. So likewise, horizontal axis is our x. So 0.8, 1.6, 2.4, 3.2, 1.0 x. Okay. So if we were to, so we know that when x is equal to 0, is 0. When x is equal to 4, is also equal to 0. So if we look at a function, you have a second order polynomial. Okay, I'm looking at this equation now. And the highest, or the x squared, is negative, means it's set phase. Okay, and you go up to minus 16. Okay, so from here, it's going to give me a set phase. No. Okay. And then from there, right, it's going to be again a set phase, right, following this function that I'm underlying now. Okay. So one thing to take note, okay, if I draw a straight line, where the shear force is equal to 0.8, you'll find that the bending moment can be either at its maximum value or at its minimum value, right? So I'm going to do 2.4 again. And the 2.4 is critical because it's going to be either be the maximum bending moment or the minimum bending moment. Okay. So I want you all to, we asked to look at equation number 4. Okay. So from equation number 4, or using, hold on, bear with me, using equation number 4, we're going to determine the bending moment magnitude. Why we use equation number 4 is if you look at 2.4, right? It's between it's between point B to point C, and we have to use this function over here. Okay, and this is our equation number 4. So I'm going to take this equation over here. Right? Hey, come on, undo. It always does that to me again. Cheeky sort. Okay, so this is our equation number 4. Right? So we're going to substitute x is equal to 2.4 into equation number 4. So m at 2.4, this is equal to minus 25 times 10 to the power 3 multiplied by 2.4 squared plus by 120 times 10 to the power 3 multiplied by 2.4 minus by 96 times 10 to the power 3. Okay, so this will be equal to minus 25 power 3 times by 2.4 squared plus by 120 power 3 times by 2.4 minus by 93 power 3. So it's positive 48 times 10 to the power 3 Newton meter. Okay. So this is at 48, right? And then at 3.2, right? So that's the maximum point. At 3.2, you have positive 32. Okay. So at 3.2, you have positive 32, right? Why I'm so bothered about 3.2 is the upper limit between point B and C is a second order polynomial equation. Then at point C to point D, from 3.2 onwards, is a linear function. Okay. So now I'm going to sketch from here. It goes up to here, and then it comes down here. Okay. I so hate this. Sorry, pardon me. It goes up to here. Hey, I think I'm better off the first time. Okay, I'm going to leave it. Okay, come. Okay, and then it comes down in a linear function to 0. This is linear. Okay, sorry, it's bothering me. My bad. Sketch properly. Okay. Right. So we know that this is 48 times 10 to the power 3. And this one is sitting at 32 times 10 to the power 3. Okay. So let's briefly look at the trend of the shear force and bending moment diagram. Okay. Let's look at the trend, and I believe you all know this. I just want to help you recall. So note, okay, as you can see, I'm going to zoom out. Okay, so when the shear force is equal to 0, okay, when I'm going to zoom in so I can write better. Okay, so when shear force intersect the 0 shear force, right? There is a possibility that the bending moment can be maximum or minimum. Okay. So maximum is at 48, minimum is at minus 16 times 10 to the power 3. Okay. But sometimes, depending on the loading condition, you can have more negative bending. More negative means more minimum value. Okay. That's why I put maximum and minimum. Okay. So this is the first thing. The second point that we take note, to apologize. I'm going to So this is the first thing I want you to take note. Okay, number A. And then the second factor I want you to take note is if you were to look at between 0 to 0.8, right? Our shear force has a negative magnitude. The gradient of the bending moment, let me zoom in down here. The gradient is also negative, right? If I'm going to sketch the gradient out, the gradient is also going to be negative. So if I pick a point here, hey, come on, Eugene, what's wrong with you today? If we're going to pick a point here, right, the gradient is also negative. You can see when I draw the gradient is negative. Then when the amplitude is positive, okay, when the amplitude is positive, like in this region, right, 0.8 to 2.4, and if I were to pick a point over here, right, I'm going to pick a point over here, you realize that the gradient is positive, right? And then when it is at 0, right, like over here, the gradient is a straight line, is 0, or what we call turning point. And then if we go from 2.4, hey, come on, Eugene, 2.4, right, to 4.0, the magnitude is negative, and you can see for the gradient, okay, over here, this is also a negative slope. Okay, so you can see a trend. So this is a way to check, right, the relationship between your shear force and bending moment diagram. So you can check over here when or the shear force magnitude is related to the bending moment gradient. Okay, so what do I mean by that is if the shear force has positive magnitude, okay, bending moment will have negative or positive, sorry, gradient. Likewise, shear force has negative magnitude, right? Bending moment has negative gradient. Okay.